Hey there, my name is Gokul, and today I'm going to be talking a bit about optimal algorithms for imitation learning in the finite sample regime. This is joint work with Nived and Rajaraman and a group of collaborators from CMU and Berkeley. So, in an ICML paper a few years ago, we showed that all offline imitation learning algorithms can suffer from a quadratic compounding of errors, which can lead to poor test time performance. We also showed that online imitation learning algorithms are able to achieve error linear in the horizon, the gold standard for sequential problems, given infinite expert demonstrations. In practice, however, we always have a finite set of expert demonstrations, which can sometimes cause online imitation learning algorithms to suffer from compounding errors. Let's go through an example of why finite samples can cause issues for online IL algorithms. Consider trying to imitate an expert quadcopter pilot flying through a forest. So they have some rollout distribution, and we observe a few samples from it. Now, because of random variation, let's say one of the trajectories we observe happens to go through a clump of trees. What's going to happen if we try to do mode matching? Well, given we're doing something on policy, we're going to try and match the expert's empirical state distribution. This means we're also going to fly through the trees, perhaps a lot more than the expert, all because of the way the dice fell in terms of the trajectories we observe. Let me give you a slightly more stylized version of the preceding argument. Consider the extremely simple MDP on the screen, where the expert always takes the action that puts them in the uniform distribution over S1 and S2. Because of random variation in the empirical samples we observe, we see more samples in S2. To try and match the expert state distribution, an on-policy mode matching learner might take the red action the expert never took, just to try and stay in S2 for longer, which is not what we want. What's interesting is that BC would be totally fine on this problem, as it is just trying to get the expert actions correct, and would therefore always pick the action that puts you in the mixture. I'd like to emphasize that this is a finite sample problem. If we saw the true expert distribution, here in dark green, we'd be totally fine. So how should we go about solving this problem? Well, if we could just query the expert for more demonstrations, we'd be totally fine. But otherwise, we need to think about how we can squeeze the most out of the data we have. To start, let's think about a tabular problem with a deterministic expert. Here, for each state, we completely know whether we have any uncertainty over expert actions. If a state is in the demonstration set, we do, otherwise we don't. Imagine if I did rollouts in the environment, took the known expert action if possible, and terminated the rollout otherwise. If I then tossed a lot of these rollouts into the demonstration set, I would be basically computing a smooth estimate of the expert state distribution for the learner to match. Put differently, I'm using repeated rollouts to smooth out the finite sample variance that results from the randomness in the dynamics. For example, it would completely fix the issue for this problem because we generate a lot of data where the policy spent an equal amount of time in S1 and S2. We call this technique of performing rollouts and then adding them to the dataset replay estimation. So the natural question at this point is how we do this more generally for problems with continuous states and actions. Our key insight is that the states where we know the expert's actions are exactly those where the BC policy is accurate. So if we're able to estimate where in the state space BC is accurate, we can then add action labels from the BC policy at those states to our demonstration set. This is equivalent to tossing BC rollouts into your expert dataset and then weighing state action pairs by some notion of confidence. So putting it all together, replay estimation is the following algorithm. First, one trains a policy via standard BC. Second, one performs rollouts with this policy, computing confidence scores along the way. Third, one adds these samples to the expert dataset. And fourth, one performs a weighted online mode matching procedure. In short, we basically perform a BC-aided data augmentation procedure before proceeding with mode matching. While this technique might seem rather intuitive, if performed correctly, it has extremely strong theoretical properties. We show in our paper that is in fact the Minimax optimal algorithm for online imitation learning in the finite demonstration regime. More formally, in the worst case, it gets a better than both worlds guarantee compared to either behavior cloning or online mode matching. We prove a theorem that applies to general MDPs with function approximation in our paper. On the practical side, we tried a bunch of different ways for estimating the confidence of BC, but what worked the best was training an ensemble of BC learners and looking at the maximum difference between any two learners in this ensemble. Empirically, this technique appears to work quite well. We can significantly outperform both behavior cloning and a strong mode matching baseline on harder variations of the standard PyBullet gym tasks. We hope that replay estimation will become a standard add-on to mode matching algorithms like Gale or Maxent IRL. With that, I'd like to thank you for your time, and feel free to reach out to Naved or I if you have any questions. Thank you again.